I pronounce your last name?
Brewhog.
Brewhog? All right, Garrett Brewhog. What's going on, man?
European.
Yeah. Yeah, dude, you just said so. You're in New York during for all future listeners. It's today the 24th, March 24th, 2020. We're in full quarantine, and you are in New York, so you got the worst of it.
Yeah, luckily I'm not in New York City.
Yeah.
I'm in Rochester, New York, I'm doing my PhD here at the University of Rochester, focused on fusion and high energy density physics. Here at the U of R, we have the largest laser of any university, and so we use that to set off essentially tiny hydrogen bombs with it. So
casually drop that.
We are just working from home and planning the future.
Yeah.
Shots canceled for right now.
Yeah. That's insane. Normally, the last couple of guests have come on, it doesn't matter who I've had on, the conversation eventually leads to coronavirus. Like, it doesn't matter what, it's just, but we've talked about coronavirus. Yeah, we've talked about coronavirus nonstop for the last couple episodes, so I'm kind of COVIDed out. But more importantly, you're the only person that what you do is, I don't give a shit about coronavirus. It's far more interesting. You're setting off tiny hydrogen bombs. You guys got a little Cold War going on in there. So
yeah. I mean, it is actually really related to it. So I don't really know what you want me to dive into. I can kind of go into what fusion is, or what.
Yeah, whatever you want to dive into, man. This is Garrett Cast. I'm a guest on Garrett Cast today. It's What is? Let's even from. I mean, I know the difference between like fission and fusion. I just from like Cold War weaponry. Fission is atomic bomb, fusion's hydrogen bomb, fusion's what powers the sun, fission's breaking, fusion's putting together. All I know is, even as someone with a biology degree who's completely not related to anything that you're doing, who hasn't heard like the buzzword like sustainable fusion or cold fusion, like that is,
Yeah. So I did my undergrad in nuclear engineering. I actually was a reactor operator at the fission reactor we had on campus, but I was very interested in fusion, and that's why I'm now here in Rochester. And the fission is great. Fission is if anything's gonna save our asses from climate change, it's gonna be fission. But fusion is interesting for me just because there's so many cool problems. It's so hard. Fission is kind of cheating. I always like to joke that fission is the only proof that there may be a God, because that's just ridiculous. Like, it's way too easy. Fusion is the right level of hard. We have to take these, luckily the fuel is really common, but you take the fuel and you have to get it just unbelievably hot. So hot that temperature doesn't make sense. Like, I can tell you the number in Fahrenheit, Celsius, Kelvin, and it'll be close enough. And you got to get up to like 100 million degrees to even hope to get fusion to happen. And then you have to have some relatively high pressures to get anything to go off. And the appeal there is that the fuel is just ludicrously common. It's in it's in my coffee right here. It's in whatever you're drinking. It's in you. It's just a form of heavy hydrogen. The sun can burn normal hydrogen, but we can't pull that off. That's kind of a cheating trick of being a giant star. But heavy hydrogen is still really common. It's called deuterium.
Yeah.
The easiest fusion reaction uses heavy hydrogen and then an even heavier radioactive form called tritium. That's what we're going for right now, because if we can light that one off, then we can get everything else to occur properly. And we've done it. We know it's possible, because if you've ever seen pictures of Bikini Atoll or any of the H-bombs, that is a self-sustaining fusion chain reaction that is occurring. The trick being is we want to do it at a scale where we can make energy, and we want to not use fission to trigger it, because we cheated. We used the most powerful energy source we knew to light off the even more powerful energy source. Well, we want to be able to light it off with something that, we don't have to put 3 kilos of uranium in every time. And that's the trick. That's why it's so hard. Once we get it going, though, then we can probably there's more advanced reactions, like just doing pure deuterium, or deuterium, helium-3, maybe even proton boron. You hear these buzzwords around. They're more advanced fuels, but we got to get the first one, the easiest one to occur before we go anywhere.
Yeah.
And the other part of the appeal being is that there's no radioactive waste left. Well, there's not no radioactive waste. You don't get fission fragments, which are the annoying parts of nuclear waste. You'll make the chamber radioactive, you'll make some tritium and other junk like that, but it's vastly lowered. And so, it's pretty obvious to see the appeal there, because if we got it to work, it's the ideal energy source. It doesn't come with the baggage of fission, and unlike renewables, it's incredibly energy dense. It's everywhere. The fuel's everywhere. We know fusion fuel wars. Let's put it that way.
Yeah.
You can you can just open your tap and you get enough fuel.
Yeah.
One tub full of seawater has enough deuterium in it to power the entire United States for something like 4 or 5 months.
Jesus Christ.
Yeah. So, and that's all energy sources. That's not just electricity. That would be like if all the energy in your car and the airplanes, trucks, everything came from fusion. So it's nuts.
That's the end game.
Yeah, it's the end game. It really is. That's why sci-fi always has fusion.
Yeah.
The two big approaches out there are magnetic confinement and inertial confinement. Magnetic confinement is the tokamaks, these big donut things that you see. There's a huge one being built in France right now. There's other twisty versions called stellarators. The general idea being is plasma is crazy hot, like I said, 100 million degrees plus to get fusion to happen. That will destroy any material known to man by a lot. Like the hottest you can get something is like tungsten at like 4,800 Kelvin.
Yeah. Well,
it's only a couple orders of magnitude low.
That's what a guy I had on the other day. Sorry to interrupt. I'm terrible at interrupting. I'm already writing down all my. I've gotten better. I got a notebook and I write down everything that's sparking in my mind so I don't interrupt. But clearly, I'm already failing that. I had a guy on the other day that worked at he's a nuclear power plant operator. We talked about fusion, and he was like, "It's not getting fusion that's hard." He's like, "We have nothing to contain it." Like, he was like, "It's." So yeah, sorry, keep going. No,
magnetic confinement. The idea being is that plasma is excruciatingly conductive. The best way to think about plasma is it's like fluid mechanics. Have you ever taken a fluids class? It's a fluid. It's a fluid that responds to electric and magnetic fields. And so that gives us an option. We can utilize magnetic fields to try to hold the plasma. The problem being is magnetic fields leak. You can't just make like a sealed jar of magnetic fields. And plasmas can make their own magnetic fields. And there's all these just ludicrous issues that we've been fighting in plasma physics to try to understand magnetic confinement. But they're making a lot of progress. A lot of those magnetic systems have gotten pretty damn good. They're just big and expensive. And I'm not the biggest fan of them, but that's more of like a personal machine preference.
Yeah.
The other big option is inertial confinement.
Okay.
And the idea, that's what we do here in Rochester. And the idea of inertial confinement is there's one way we know fusion works, and that's the bomb.
Yeah. Yeah.
Goes off by, you set off a tiny uranium or plutonium bomb. And it uses all of that radiation pressure and compresses the fusion fuel and lights it off. But we know you can just quite literally compress it, just like a diesel engine, and make it happen.
Yeah.
Right? Stars are actually kind of similar to that too. Most of the fusion, or basically all of the fusion, is only happening at the very center of the star, where the pressure is very, very high. So the idea is, what if we just compress it really hard? And in kind of holding similar to an internal combustion engine like a diesel engine, you make everything temporary. So you don't have to control it. You just let it explode. It doesn't matter because you didn't give it enough fuel to damage the reactor. And you can have peak temperatures that are way higher than the materials, and you can use all sorts of tricks like that. Like your car has a peak temperature in the gasoline way higher than the steel can handle, but it's only, it's going like that, up, down. And so your car, the average temperature is lower. And so the initial idea there was that we had to come up with somewhere to compress it that wasn't an A-bomb. And they started out with what's called a Z-pinch, and that's still being done. And that's where you use just a huge current, like millions of amps. And you get this J-cross B force where if you take E&M, it's like that, squishes in, the magnetic field collapses the plasma, but instabilities form. It's the same magnetic problem as before. Then, in the 60s, we invented the laser. And everyone went, oh, this is the trick right here. And there's a very famous paper. Supposedly, this was talked about even older. There's a famous paper from John Knuckles outlining the idea of laser-driven fusion. As the story goes, it was actually inspired by conversations from like the very beginning in the hydrogen bomb program with Edward Teller, where he said, "I think this laser thing is going to do it. We just got to let it develop." And the idea there is that you can have a pellet of fuel, and lasers come in from all sides, and they'll ablate the fuel off. You got to have the fuel in some sort of casing, right? So the way that we make our pellets is we have a little plastic outer shell. We freeze hydrogen on the inside, fuel hydrogen, and then we burn off the plastic with the lasers. And if you think about it, that burnt off plastic only has one direction to go, and that's back outwards, and it's really, really hot. And that is exactly like if you had a ton of rockets all the way around the thing. So now you have, in our case, we have 60 lasers. We have 60 rockets going on that fuel on all sides.
Okay.
It collapses in at hundreds of kilometers per second. Yeah. And there's a little bit of gaseous fuel in the middle. And when all of that comes in, it's like a diesel engine from every side.
Okay.
Presses it up, gets it really, really hot, and bang, it explodes in a small fusion explosion.
Okay.
So the trick there is we're still understanding some of the instabilities and issues. There's two different ways of laser fusion. Now they're trying to mix magnetic fields, but we're getting close. Both methods are they're within about 70% of what's needed to actually make this happen, which is pretty exciting. I would say within our lifetime, we'll see it happen. We'll see a beginnings of power plants and things like that. We're no longer in the fusion's 50 years away. We're in the fusion 10 to 20, depending on money.
Yeah. Yeah. If I heard that quote that says fusion's always 40 years away because that's how long a career is. So you just got to keep it on the table for 40 years and then you can retire and go, I don't know. And then the next guys come in and go, ooh, I can get 40 years of a government paycheck. Yeah, fusion's 40 years away. It's like fusion will always be 40 years away.
Sadly, that's there. That is an issue. That's an issue in science, and that's especially an issue in fusion. Yeah. And part of the reason that that's there in fusion is, you notice the way that I described that goes off, I said, it's just like the hydrogen bomb, similar to a hydrogen bomb. Well, a lot of our funding comes from defense applications because we haven't set off a nuclear weapon in 20-odd years. And our bombs are pretty old. They're mainly from the 60s. Sure, like to be sure they work, but we have no way to test them. So what we have to do is make sure our models of how a bomb works are really good. The only way to test models is to do experiments. And now in the U.S., we're actually upgrading our arsenal. We're not doing like a full rebuild, but we're like, stuff's old. Yeah. It's just like if you had like a muscle car, like an old car from like the 60s, and you need to just go through, change out all the seals, do all this different stuff, do the bat. Yeah. Yeah, because we've got all those. I mean, I think it was I want to say it was at either the tail end of the Bush administration or the tail end of the Obama administration. But yeah, there was like a big thing that like no one really talked about, but it was like we set aside like $1 trillion, and it was like we got to revamp our nuclear arsenal. And everyone's like, why do we need to do that? And it's like, dude, these things have been sitting there since like the Kennedy administration. And a lot of them are really, really old. The newest ones, I think, were 85 or something like that. It's like, would you trust, like, you think about like a car. Would you trust a car from 1985 to just start? Yeah. And it's, I mean, and the whole point of the nuclear weapons is like, no one's going to use them. It's the deterrent. But, if you're everyone, you need to be sure they work for the deterrent. If you're China and you're coming up into the world and you're throwing some elbows and you're going, hey, I'm not sure if those MX missile systems work. They haven't fired them in 30 years. If there's ever going to be a chink in the armor, that's it. It's, I mean, how old are the Titan IIs? Like, I mean, the Minutemen are, I think those are a little newer, if I'm correct. Minutemen 2 or 3, I don't know. I think there's a replacement program happening now. I mean, they're just old.
Yeah. Yeah, they're old as shit. And I remember seeing something that was like nuclear weapons are unique, and then it's like they have there's some stipulation where it's like they have the always, never requirement or something. And it's like they always work. Well, they'll always be able to be fired. And of the ones that are fired, so 100% will have to always be able to be fired on the first try. 100% of those will always have to work. And 0% of those can ever go off by accident. It's like we don't have that stipulation for anything else. Like not JDAMs, not grenades, not M16s, not it's. But with these, it's an always never.
And on top of that, if you look at like the M16, for example, right? Sure. It's gone through tons of evolutions. Now we have this very reliable, good rifle.
Yeah.
Because we've tested it in the field. We've tested it, modified it, done it. The number of nuclear weapons that have ever been set off, talking like 1,000 or 2.
Yeah.
Most of them not even at full yield.
Yeah. Yeah, we stopped doing the insane experiments. I want to say, when was the Non-Proliferation Treaty? Was that 63 or 73?
The test ban. So there's been a bunch of treaties. The newest one that stopped all of the testing was in 93, I want to believe.
Okay.
93, 94, somewhere in there was the last detonation. And that was because of the test ban treaty. The other treaties were in the 50s, 60s, even into the 70s. There were treaties that limited things. Like we stopped doing above ground testing, I think, in 61.
Mm-hmm.
So the famous, like, go out to Jackass Flats in Nevada, set up a chair, and just watch these and collect your eyes.
Put the goggles on. Yeah.
Yeah.
Yeah. Yeah. Some of those old pictures of the Pentagon elite sitting out there in like rows of chairs with like their suits on with the goggles on, those look like album covers because they're sitting there and it's just like you just see flash reflections in their goggles. Those are some badass pictures.
Well, that really helped kick off Vegas, right? Like people would go to Vegas specifically to go watch them go off.
Yeah, I plug it almost. It's becoming a running joke that it somehow manages to weave its way into every single episode. But Raven Rock by Garrett Graff is an awesome book. I think it was the #1 seller on Audible last year. I'm trying to get him on the podcast. But it's all about the nuclear bunkers underground. Or, yeah, obviously underground. The entire relocation arc of everything. But it goes through the history of nuclear weapons. And they even talk about, like, said in, like, the 50s, it was part of the draw. Like, because you'd go to Vegas, right? And so you got all your big city slicking cars, all the women with the huge hair. But, yeah, it used to be a thing where you could kind of start to gauge, like the casino and hotel owners could gauge when a test was coming because they'd see like increased military convoys coming in. They'd see increased like choppers and planes and they'd be like, oh, there's going to be a test this weekend. And so they literally used to be like owners of the huge casinos would be like, hey, like wake up at like 4 tomorrow and like look that way. Apparently people used to get up like, cigarettes and brandy, like breakfast, and they'd watch and they'd be like, they never knew when, obviously because it was all classified. But there'd be like, there's going to be a second sunrise over there. And there'd be a flash, there'd be the boom, and then you could, granted, these ones are in still like the kilotons, but like, then they see the mushroom cloud rising. I was just like, is that not the most like metal thing ever? Like,
yeah, I got to be honest, I'm not a fan of the idea of above ground testing, but if they were ever going to do it, I'd be out to Nevada.
Oh, no, I'm with you. It's horrible for the environment. That being said, if there's going to be one, I don't know if you ever look at like the atomic testing videos on YouTube. There's always people that are like, can we just void the treaty for one afternoon so we can film this in 8K? It's like, can we please get some GoPros, some 60 FPS? Can we please just like, and then we'll do the ban again. We'll stop doing it. But like, dude, even somewhere like the Castle Bravo tests, like even with those cameras, it's still awe-inspiring. And it's like, oh.
Well, that's Castle Bravo was so big.
15 megatons. Yeah.
You can find the crater on Google Earth because it cut the island in half.
Yeah. Yeah. It was. Yeah. Yeah. It's, dude, there's the most badass description ever in a book by Annie Jacobson. And I always mention books. I don't read. I listen on Audible. I play video games, but I mute it and I listen on Audible. That's the only way I learn. So no, but it makes me sound smarter. I'm like, I've read this, but no, I'm listening while playing Modern Warfare. But DARPA by Annie Jacobson, she begins with the Castle Bravo test, and kind of how everyone was nervous and everything. And there's like, the timer or the announcer, and it's like 2 minutes to 0 hour or 0 time, and they go up there and they're talking about how all the staff is up on top of the bunker. I think like Rongelat, whatever the island was, and they've all got their big goggles on, and it's like, put your goggles on now. And one of the older guys, apparently one of the senior guys, was like, all of a sudden he started cursing, and they're like, what? He's like, he forgot his goggles, but there wasn't enough time to go back down to the bunker, get him, and come back up. So he either had to go back to the bunker or he just had to turn around. But he was really upset because this guy was like 90, and this was in like the 50s, and it was like, is he going to be able to see another one? I don't think he was like I don't think he was like Teller or like Ulam, but he was one of like, he was a contributor. And there was one of the younger guys that was there. I don't know, maybe your age, my age, and he was like, I wasn't one of the contributors to this. Like, I'll see more in my lifetime. So he gave him his goggles, and but he knew that he didn't have to go back inside, but he knew that he couldn't face it. So, and this is the most insane description ever of like the kicking off of the thermonuclear. But I don't know, Castle Bravo wasn't the first one, but still,
it wasn't the first one, but it was one of them.
It was the big boy. It was 15 megatons. It wasn't supposed to be, but so he talks about turning around, and just the imagery is insane. So he says, like, lined up on either side, as far as you can see, it's like 50 on each side. Are all these scientists, right? All the white coats, the military generals, the 4 stars, it's just the whole, it's like Dr. Strangelove. And they've all got their black goggles on. And he goes, so while they were watching the hydrogen bomb go off, I was watching them watch the hydrogen bomb go off. And I guess, what is it, the Teller light or the whatever it was? It temporarily...
Teller light.
He goes, for a couple, maybe it felt like a couple seconds, maybe it was a couple seconds. I think it was only like a brief. But he goes, I looked both ways, and I could still see all their clothes, but he goes, they were just skeletons. I couldn't see skin or muscle. I was just looking at skeletons. So he goes, I'm looking both ways, and I'm just looking at these rows of skeletons and teeth and like, sockets in the jaws, and they're all wearing goggles and they're all wearing like white coats, and I was just like, is that not the most insane like imagery? Like, is that's some shit straight out of Hollywood? That's like a Quentin Tarantino movie, or like, it's like, just imagine looking, it's just like, you see like the teeth and like the no hair, but it's just goggles, and there's in each lens he could just see Castle Bravo rising, and I was like, dude, that is like if that was an opening to a movie, you'd be like, that's too fantastic. Like, I don't believe that. Yeah. But yeah, I don't know where I was going with that, but have you ever read Dark Sun by Richard M. Rhodes? It's about the hydrogen bomb.
I've heard of it, but I haven't read it.
Again, Audible. I don't actually read.
Yeah, a lot of my stuff is I've read so I'll give you some recommendations.
Yeah, please do. I was going to ask you that, actually. That's where I was leading into.
I recommend the Los Alamos Primer, or another option would just be the Making of the Atomic Bomb. I think it's by Rhodes.
I've read that, yeah.
The Los Alamos Primer, he does an opening for it, but he didn't write it. It was one of the Los Alamos guys wrote it.
Yeah.
It was what they would hand everyone when they'd show up, because no one came with any knowledge of what was going on. It was just these running notes of what they had figured out and what they thought was possible.
Holy shit.
And then just like weird insight into like, this is what it was like.
Yeah.
And then another really good one is the Memoirs of Edward Teller, which are just his memoirs right before he died. And he talked about everything that he was part of. And it's just interesting because he was a very complex man.
Yeah.
He had he's got an interesting kind of collective memory in our culture. And learning more about where he came from really kind of drives home why he was the way he was. Yeah. Because apparently he was born in Hungary, Austria-Hungary, when World War I started. And they were monarchists. And then they lost the war. They became communists. Then he moved to Germany, and he lived under fascism, and then came to America, and he was Jewish. His family was persecuted under both the communists and the fascists, and it really kind of drives home why he was so freaked out about the USSR, why they scared him so badly.
Yeah.
Because he knew we'd killed the Nazis. He was there for that, but the commies were still there, and that really... I think that because he experienced that at such a formative age, I think he was like 16 when his dad's business was taken from him or something like that. Like it was all kind of nuts.
Yeah.
I think that was just in his mind forever.
Yeah, he kind of gets shit on as being the father of the H-bomb, and made fun of in Dr. Strangelove, and everyone's like, oh, who's this, Dr. Tala, of course. But it's Annie Jacobson talked about that in DARPA. She was like, he grew up like seeing firsthand what happened. And so when he came to the US, the reason why he never slowed down, and the reason why when, Oppenheimer was like, we don't need anything past the fission bomb, like we don't need anything more than the kilotons, That's why Teller was like, no, we need this, not because we're going to use it, but because if we don't have it and they do have it, they will use it. And he was like, and trust me, there's nothing that they won't use. The only reason they haven't used it is because they don't have it yet. He was like, I've seen firsthand. So where all of us was like, no, it's, we don't know anything other than America. He was like, you don't realize, like, he was like, this is like an island fantasy what's here. And he's like, and it has to be protected with the biggest sword possible. And the biggest sword, he was like, is hydrogen bombs. And he was like, yeah, so it's, you have to know his history and where it came from to understand his, admittedly obsession. But
because you're right, he does get painted as very bloodthirsty, but he's got some fun insight on Oppenheimer and some of the other guys where they were also a bit bloodthirsty at once. Like, Hitler was very against dropping the bombs on Japan.
Yeah.
He would do a show. He pushed really hard to either develop air bursting, which we had not yet figured out, but he said, take the time, just develop it, scare the shit out of them, detonate the thing over Tokyo, break all their windows, terrify the emperor, or he said, let's bring them out to an island and let's just blow an island away.
Yeah.
Because he felt that just using it was a less ethical move than showing them, giving them that chance to surrender.
Yeah.
Which is kind of funny coming from this supposedly very bloodthirsty.
Exactly. No, Teller was not like that. Well, Teller did have some comical ideas. I think it was, I forget the names of them, but he had the code name for these 2 bombs he was developing that even the Air Force turned.
Backyard bomb.
Yeah, the backyard bomb, 10 gigatons. But I didn't know this. His code names for them were actually the Latin names for ancient sundials. because everything would cast the light from it. And I was just like, that's so fucking badass. He's like, why are these named that? He's like, well, it's the backyard bomb. Like, why? He's like, you set it off here, it'll take out Beijing. It was,
He actually, apparently, I only found this out rather recently, but he apparently pushed at the end of the Cold War to have U.S. and Soviet scientists get together, because right around then, there was a comet that hit Jupiter or something like that. Anyways, it was kind of in everyone's mind. The idea of
Shoemaker 9.
Yeah. And he said, hey, let's get everyone together. All these, nuclear scientists will give the Soviet guys a job by having them work with our guys to develop a giant space safety bomb, basically. The idea being like you could deflect huge things with a big nuclear bomb. You just need to have a big enough one. Because right now, all of the asteroid deflection projects, a lot of them do assume nuclear weapons, but they still need quite a lot of warning because the nukes aren't all that big. And when you're talking about a rock the size of, Manhattan, it takes a lot to move. Like a nuke is nothing. That's always the funny thing to me about nukes is they're both under and overplayed in how powerful they are.
Yeah.
There's this whole thing of like everyone assumes a nuke is just end all be all, and that's not true.
Yeah.
Nature has got us beat handily.
Yeah. No argument. Yeah.
You look like the Yellowstone super volcano. It's like nukes are nothing.
Yeah. Yellowstone is like LOL. Like oh, you got our bomb book? Cool. Yeah. That's another thing I've heard is like the idea of shooting up like a 500 megaton nuke at an asteroid. They're like, all you're doing is turning a rifle bullet into a shotgun.
Well, the point being is to not don't blow it up. That's the one thing that Armageddon got wrong.
Yeah.
You actually set the nuke off nearby in a blade and push on it.
Yeah, push it the other way.
I don't know if you've ever heard of the Project Orion, but there was a whole thing about basically that.
Yeah.
You need to do that to an asteroid.
Yeah. Yeah, Project Orion was insane. What about I was gonna say, do you ever heard of Project? I don't know how to pronounce it. Daedalus.
Yes, the later version out of the British Interplanetary Society to make an interstellar based on ICF, inertial confinement fusion.
Yeah, they wanted that thing to get going to, I think 14% the speed of light.
You could do it.
Yeah,
that's within the capability of fusion. Their ignition scheme wouldn't work. We now know that. The way that they were going to make the fusion reactions happen. But otherwise, it would have done it. That's kind of the beauty of fusion is that it's another advantage it has over fission is that the amount of energy released per unit mass is higher, and the particles that come out, the exhaust, if you think about it, the rocket, are faster. And that is how you make rockets go fast, is high exhaust velocity.
Yeah.
The higher the exhaust velocity, the faster you can end up going. If I remember right, you can do something about, if you use a lot of fuel, if you had a nuclear rocket with roughly the same fuel ratio as a chemical rocket, you would be looking at something like twice the exhaust velocity that you could reach.
Yeah.
So the fusion particles are coming out 7-ish% the speed of light, then you can push up to 14.
Yeah, dude, I had a guy on from JPL, and he's making something called MemeSat. It's just gonna be a CubeSat that just beams back memes. But yeah, but he and I got talking, and we're just talking about like the fastest possible speeds. We were talking about like Voyager, and then we were looking up other like Helios 2. I think got to 100, he kept chastising me because he's like, you're using American units. Like in space we use metric. It's like so please excuse me, but I was like, yeah. So we looked up Helios 2 got to like 150,000 miles an hour. And that was in like the 70s, and Voyager 2 I think is going 38,000 miles an hour. And then the Parker Solar Probe, which I guess we launched at the sun, that one's going like 450. But so we started talking about like, what if we just got some like stupid money, just like had like $1 billion to throw away. We weren't accountable to any space agency or private industry where it's like there has to be a purpose to what you're doing. SpaceX, it's like,
how fast can you make it go?
Exactly. So we started talking like, well, what would you do? We're like, let's say, so we said that there's no destination, so we don't have to worry about what has to go in that direction. It doesn't even have to be in the plane of the solar system. It can go wherever. Mm-hmm. So slingshot it around as many planets as you can, and then the actual satellite itself, it would just be, we would strip it of everything except a radio beacon powered by like a nuclear power plant reactor, so it never died.
A little RTG, a chunk of plutonium.
Literally, it would just so it's, and it would just send back its beacon. It would just beep beep, and we could detect its distance just by using like the Doppler effect. That's how far away it is. So we don't need to worry about, because like Voyager, they're slowly shutting down, if they haven't already. Like they've been, over the decades, they've shut down this system and shut down that system. And
well, yeah, she's running out of fuel.
Exactly.
Been going for 40 years.
Yeah. It's almost been going for 50 years, 72. So we talked about, we're like, all right, well, what we would do is we put like a plutonium reactor on it, and it would just have a radio beacon, super high powered, but just nothing else. No cameras, none of that, all that other instrumentation. And we'd strip everything else, and it would have a giant ion thruster on it. And we've been talking about like, all right, so we looked up like the newest xenon ion thrusters, and apparently they can get something insane like 48,000 hours of fire time. So, but we looked up that the reason why they eventually stop is because the like the grid, whatever that they have, some
cathode erodes, right?
Yeah, it erodes, and they said so. It's not the actual like xenon. It's because xenon's, I mean, compared to like kerosene, it's light, right? So we're like, what if you did a staged xenon thruster, where you had one that burned for 48,000 hours, and then you booted it, fired the next one, you had 3 of them, and at the very tip was just this radio beacon. How fast do you think we could get it if we just slingshot, and its sole purpose was speed? It's not like, because when you bring up speed, they're like, well, it's still going to take you 40,000 years to get to Alpha Centauri. We're not going to Alpha Centauri. It's just speed. There is no destination. Yeah. And I mean, the way to go would be to use some sort of like fusion reactor, wouldn't it?
You would actually use direct fusion exhaust, because the exhaust from fusion is faster than the exhaust from an ion drive.
Yeah, because ion is what? I think 70 kilometers a second is how, or maybe 90. Yeah. I think it's 90 kilometers a second. How fast is fusion?
Slow.
Hold on, you're breaking up. You there, Garrett?
One other fun one for you. I don't know if you've ever heard of the nuclear potato gun that happened at Los Alamos.
Is that the manhole lid?
Yep.
Yeah. How fast did that? Yeah, explain that for people listening.
No. Okay. So they were starting to do the first ever underground tests, and the idea being is you dig a hole down into a big cavern, And you want to be able to drop stuff in, because we don't just set these bombs off and go, wow, it happened. You know, we want to have diagnostics. We want to know how well it happened, blah, blah, blah. There's a bunch of physics. We even learned a lot of physics out of setting those bombs off. Essentially the whole field of high energy density physics came out of that, which is studying matter at extreme states, like at the center of the Earth, center of stars, things like that. And so they have this big ass hole, and they don't want all the radioactive exhaust to come out, so they put a big manhole cover on it. It's huge. I think it was like 20 tons of steel. And the idea was that, well, you know, we did the rough math and it won't throw the cover off. Their only concern was that it might go like this and leak. Yeah. And so they put a high-speed camera on it to look for any leakage. And they set the nuke off, and the camera, it was really, really fast camera. One frame caught that thing leaving. And so the estimates were just ludicrous speeds, but it was far beyond escape velocity. They think it just actually turned into plasma and dispersed in the air. But if not, it is the fastest man-made object by quite a lot.
Yeah.
It handily outruns the Parker Solar Probe.
Oh, yeah. No, I read something that said it would have been going like Mach 200,000 or something. Like, yeah, it's not even in the realm of like anything that we can like relate to. It's like,
and that drives home the incredible capability of something like Project Orion or Daedalus, where you really directly use the nuclear energy, not like the current nuclear rockets that are being researched, where you use a reactor, you heat up working fluid and run it out the back. Those are great. Those are going to probably be what takes us to Mars. But, you know, you compare that to directly using the nuclear energy, and it goes from, well, it's faster than what we currently use, but still pretty crappy, to Star Trek crap.
Jesus. So the meme sat, not the CubeSat, but the one that we want to just go where nothing has gone before. What would you use fusion for that?
Oh, if you wanted me to make the absolute fastest thing,
just absolute fastest. But we can't. We want it to be somewhat realistic, because we can't just be like, unlimited price tag.
I wouldn't use fusion, because we're not there yet. Yeah, I would use Project Orion.
Yeah,
I would send nukes behind the thing.
Yeah, but I don't think so. But like, we couldn't get that, like, because we couldn't get access to that. We couldn't get just some assholes like us. We couldn't get it.
I'm not accountable to anyone, so I'm gonna assume and get the nukes.
Yeah. No. Yeah. See, if there was like truly no, the thing is like, I'm kind of looking at this as like, I wonder if it could be done. I wonder if it could be like a crowd-funded meme set. If we did get the money somehow over 20 years,
we'd never get the plutonium.
We would never. So we couldn't use, because that would just be, it wouldn't matter how much money you had. If you're not a government body, if you're not a nation. You don't have to be
a government body to get it, but you do have to jump through all the hoops. And especially in the Western world right now, nuclear is not an easy thing to get through.
Yeah, no one's gonna give me nuclear weapons.
Another option would be beam propulsion, like with the Star Launch. Is it Star Launch? I can't remember the project where they're talking about making a huge laser to push these little nano satellites out to Alpha Centauri. That's a very viable option.
Really?
It totally works. You just need a gigantic laser. Now, I think they're going to run into problems not with laser tech. Laser tech is very mature at this point. The problem is no government's going to be a fan of some private company having 100 gigawatt laser.
Yeah, because that's very quickly you become a world power with that.
Well, let me put it this way. The Navy's current most powerful laser that they have on a ship is 150 kilowatts. Jeez. So you got to go up to hundreds of gigawatts before this becomes viable.
Okay.
That is a lot more than shooting airplanes out of the sky. That's like melt ships, burn bunkers, sci-fi sort of stuff.
Okay, yeah, so that's not doable either. So you mentioned earlier, I wrote this down, you mentioned the Z pinch. Is that what's used is that the Z machine?
Yes, that is the Sandia Z machine.
I always remember that image from the Guinness Book of World Records.
Yeah, she's a beauty.
Yeah.
I guess I'll go over a little bit of the Z machine and the inertial confinement in the U.S. So the U.S. leads in inertial confinement by a lot, and it's primarily because of our national security interests. But it does mean that there's a good chance that if we do get fusion to ignite with inertial confinement, it'll happen here. There's actually an excellent chance. I think the only other option might be China. No one else is anywhere near. And the 3 big facilities we have are here in Rochester at the Laboratory for Laser Energetics, which is just an enormous university lab. Really, when you go into it, it looks like a national lab. Like if I didn't tell you it wasn't a Department of Energy lab, you would just assume it is.
Yeah.
Where we have 2 huge lasers, one of which is set up to do 60 beam compression. It's called Omega. It can do essentially any version of inertial confinement. We even have a way to bring magnetic fields in, which is kind of cool. And then its sister is Omega Extended Performance, which are 4 very large beams. They're much more powerful than Omegas, and they do other compression experiments. And one of them can be piped in to essentially act as a heater. Okay. With the idea being that you compress, but the problem in inertial confinement, it's really funny. So magnetic confinement has no problem with temperature. They'll easily drive the temperatures up hot enough for fusion ignition. They can't get the densities high enough. In inertial confinement, we can get the density fine, easily. We've outran the density in the center of the sun at this point. We can't get the temperature high enough.
Yeah.
And so the idea with fast ignition was, well, what if we compress? When we bring one more extra laser in, and this laser is different. It's not meant to compress. It's very fast, and it's meant to just add some extra oomph,
Yeah.
It's a little like a spark plug.
Yeah.
And that's the Omega facility, or the Laboratory for Laser Energetics facility. The Z machine is in Sandia National Lab down in New Mexico. It's a mega amp. It's 26 mega amps, so millions of amps, Z-pinch, and it just drives lots of current straight down. The new thing that they do is called maglith, and that's where they set a magnet, like a normal magnet, already. The fuel's in there, nothing's lit. They heat it with the laser, so it gets cold by plasma physics standards, but it is plasma at this point because the fuel doesn't start as plasma. And the magnetic field gets locked in. And quite literally, it's like it's frozen. And then they drop the Z compression. And this helps mitigate the instabilities that I talked about. There's these terrible magnetic instabilities in the Z pinch. They're very classic. They're a classic plasma physics problem called sausage and kink. Those are the 2 big ones, where it quite literally looks like a bunch of sausages rather than this tube of plasma that should be linear and just easy compress. It's like squish, 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 and then kink is where the squishes bend.
Okay.
And that sucks energy from the machine. With this maglith scheme, they're doing a lot better. They're making incredible strides, and I have a lot of hope for Z-pinch. I think that one's got a lot of potential. And then the final facility is the National Ignition Facility down in California at Lawrence Livermore Laboratories. It is a 2 megajoule laser. So Omega here is only 30 kilojoules. NIF's a tish bit bigger.
Yeah.
Largest laser in the world by a lot. Like easily the largest laser in the world. And they're only set up to do what's called indirect drive. So we have here with Omega, we can do direct, where we just directly burn the capsule, or we can do indirect, where we put the capsule in this little hole ROM. It's a little tube, basically an oven. The idea being is that lasers are not actually smooth. If you ever look at the beam spot of a laser, there's all these little hot spots where it's more powerful there than there, and that drives the compression to not be equal. So you can think about, like, if you were squishing Jell-O with your hands, you would have spots leak out, and that's bad. What is smooth is the way that a bomb does it, which is with X-ray drive. The bomb just literally heats up everything around the fusion fuel, and then X-rays come off because it's so hot. The X-rays ablate the fusion fuel in an H-bomb, and that compresses it, and that's smooth.
Yeah, that's the 360-degree rocket you were talking about.
Yeah, similar. So for indirect drive on NIF, they have this tube where the little pellets inside this tube of gold, and they bring the lasers in from 2 sides, and they hit all along the tube, heat the whole tube up to thousands, hundreds, maybe million degrees. I don't know, really hot. It emits a lot of X-rays, and then the X-rays ablate the little fuel pellet rather than the laser directly.
Okay.
that is very similar to how a bomb does it, and so that's why NIF does it that way. It's for stability reasons. At the time when it was built, it looked like it was the best option. Now we're not so sure, but also it really does help with the national security initiatives. It really does help us study how an H-bomb works and make sure we understand it. There's a talk now of reconfiguring NIF to do direct drive, because here in Rochester we've made incredible strides at direct drive. We've increased our fusion yield by something like a factor of 10 or 20 in the past couple of years by just understanding how to do it better.
Jesus Christ.
So it's, there's like I said, there's hope. NIF is very interesting because NIF is the first fusion experiment to have seen multiplication, which means one fusion reaction helped make another one happen.
Oh. Okay.
So we're like on the cusp. We're on this annoying point of like, we know we're so close.
You're on the 1 yard line.
Yeah, on the 1 yard line, basically. And that's why there's this whole push of like, what can we do at NIF to make it happen? Because NIF will never be a power plant. It will never work for that. It's got so many problems. It can only shoot 3 times a day. It breaks itself all the time. All sorts of issues. But if we can just study a burning plasma in a lab, it's gold.
Yeah.
It'll help everyone. It doesn't matter magnetic, inertial. It will just be helpful to understand what's happening.
So is that, you said the multiplication. So is that a huge milestone in fusion, I guess, energy research?
Huge.
So, I mean, that's kind of like full circle. It's kind of like coming back to like chain reaction. Like
it is. That's the
radioactive pile.
Chain reaction.
Yeah.
Just like with fission.
Yeah. Can we get 1, 2, 4? Yeah.
It's kind of the Chicago pile moment.
Yeah. Yeah.
It's happened. It's just not happened. It wasn't it was like a subcritical chain reaction. It's like we saw the chain. We know it's doing more than just the energy put in would make happen.
Yeah.
But it's not
died out.
It hasn't ran away. And that's actually kind of the beauty of inertial confinement is we want it to run away. Unlike in fission or in some of the magnetic schemes where you need to hold it, you want to keep a steady chain reaction. In inertial, we don't care. We want it to burn all the fuel. Sure. Yeah. That's great.
Go for it. Yeah.
We only give you, our fuel pellets, so at Omega, our fuel pellets are less than 1 millimeter in size.
Oh, Jesus.
There's so little fuel in there. NIF's fuel pellets are only 1 millimeter. But the idea being is that 1 millimeter fuel pellet, if it was actually ignited, would release something like 2-3 megajoules of energy.
Jesus Christ. So is there a way, let's just entertain this stupid idea. Is there a way in an ideal world where we could, so you talked about like not wanting to use a bomb to set off fusion, because that's what, so with fission we take, I know the very first one, we had specially machined explosives all around it.
That's still how it works.
That was for fission, because there's gun type and implosion type, and then with the first H-bomb, I think that was Ivy Mike. That was the where it was just like
it was an A-bomb.
Yeah, with a tube of like deuterium or something. I think there was some tritium in it, and it was like literally we're using an A-bomb as a primer.
That's actually how all H-bombs function.
Yeah,
they all have an A-bomb in them, and the A-bomb is the same, special explosives and everything. So I'm guessing what you're getting at is, could we set it off with explosives?
Yeah, can we get to that point?
So there are theories about how to do that. The issue being is that chemical explosives just don't seem to have the energy density.
Okay.
There are some theories about what are called super explosives that might allow us to pull this off, but nothing has shown up right now. And that's actually why the lasers are so key, or the Z-pinch are so key for this, in that a laser can take, all of this energy. So if we're going to talk about like an Omega laser beam, right? Each beam is 500 joules. It takes that 500 joules and it puts it down into an area that is something like 1 micron in diameter. That's a very high energy density.
Yeah.
Chemical explosives just don't have the capability to do that. On top of that, they'll still run into the heating issue. But that's not to say it's not possible. Like, who knows? Maybe someone comes up with something in the future. Personally, I hope not. because then that would give you pure fusion weapons. It would be much harder to control. The main way that arms control happens right now is preventing people from getting the plutonium or uranium needed.
Yeah.
Fusion fuel is a little bit easier to get hold of.
Yeah.
And so I'd rather that not ever occur.
Okay, fair enough.
Personally.
What about, one thing I've looked up before is I was watching, do you ever watch the Slow-Mo guys on YouTube?
Mm-hmm.
Yeah, they got some badass videos. And that's where I've actually learned like what a shape charge was, because I'd always heard it before, but then I saw it and they did like a test of the shape, like a non-shape charge versus like a vault door, and then a shape charge was a vault door. The vault door, I mean, it literally just pokes through it like a fucking knife through butter, just nothing, because it's all concentrated.
Yeah.
Yeah. Let me know when you gotta go, because like I said, I'll keep talking forever. And so then I started looking up like, what about a nuclear shape charge and something called the Casaba howitzer? Would you use that for fusion? Would that work?
Well, I mean, you already have the nuclear bomb, so yes, it would of course work.
Yeah. So
there are some kind of wild ideas involving nuclear shape charges and fusion, and there's some pretty interesting stuff involving making like detonation waves and things like that, where you could actually make a Casaba howitzer with a pretty, because it's shaped like it's still pretty like boom.
Mm-hmm.
From declassified stuff, we don't really know. There were tests done. The Army knows, but there's some very interesting papers specifically from a guy with the last name or the name of Friedhart Winterberg, who talked about setting off a deuterium burn wave and making what he calls pencil bombs for mining. And they would actually have much more of like beam rather than shotgun, which is wild.
Was like, how do you say it? Is it Casaba?
Casaba? I'm not entirely sure.
Yeah, it's a weird one. Casaba. Do you think that's what we would have used for SDI, Star Wars?
It was part of it. There was a lot of things in Star Wars that were all planned to be tested, including bomb-pumped X-ray lasers, Casaba howitzers. There was one where they would do that. They would have these basically like tungsten shotgun pellets at the end of it. Huge chemical lasers, huge particle beams. I mean, there was a lot of very cool stuff that was talked about for that, and a lot of it tested, and a lot of those test machines are actually now research machines. I personally worked with stuff from the Star Wars project that we're now using for research, which is pretty cool.
That's insane.
Kind of wild. I mean, it was a weird project. There was a lot of questions about if it was the right thing to do. But from a scientist's perspective, it's like, we could do a little more Star Wars. I like all that money.
We could inch a couple. Yeah, we'll revive Reagan. Now, there's something else I remember reading like years and years ago. But I remember thinking, I was like, this shit seems like science fiction. But I think it was called like the Shiva Star.
Oh, that was a big pulse power system that I think it's still at Los Alamos.
Yeah, I remember reading it, and I thought it was a typo, but they're like, it'd shoot balls of plasma.
Oh, Marauder,
yeah. Had SDI
That's one that gets brought up quite a lot. So me personally, it's pet peeve of plasma weapons are a pet peeve of mine because I've studied a lot of plasma physics.
Okay.
Projecting plasma is kind of a bad idea unless all you want to do is cause electronics damage, which is the main thing Marauder did. The problem with that is plasma at its core is hot gas. So its density is low and it doesn't transfer its thermal energy all that effectively. So you just imagine if I threw a ball of gas at you, it would go poof and it wouldn't do all that much. Now the electronics damage, plasma can basically make an EMP on target, is pretty cool. But the better way to use plasma as a weapon is to bring the plasma or make the plasma on site, aka a nuke or a laser. But Marauder was kind of neat in that they did mess around with self-stabilized Spiromax and see how they launch. And, a lot of very fun stuff that actually might have some applications for fusion. There's now a group doing what are essentially Marauder guns all pointed inwards at each other.
Some fucking mad scientist shit.
Yeah, it's pretty cool. It's this new area called magneto-inertial fusion, which the idea being is that inertial's had its problems, magneto's had their problem, magnetic confinement's had their problems. Maybe we can get something by mixing them.
Okay.
And so that's what that's where like all the hot new work is.
All right.
Anyway, I need to go.
Okay. All right. Okay. Will you do another episode sometime?
Yeah.
Fuck yeah.
Point, definitely.
Yeah, dude. I've literally got a page of questions written down. All right. Yeah. I'll let you go. I'll save them for the next one, dude. Let's definitely do another one because this was awesome. Like instead of having to like scroll through all the Wikipedia pages, I'm just sitting here with an actual fusion scientist. Perfect. You're entertaining my stupid monkey brain.
In training right now, I'll only claim nuclear engineer for the moment.
Either way, it's light years above me, man. I failed pre-calculus 3 times. All right, so this is good enough. All right, man. Hey, stay safe out there. Keep isolating, and if coronavirus doesn't kill us all, maybe there'll be a utopia powered by cold fusion. Who knows? But all right, dog. Stay safe, man. Peace.
You.